And all right, I'm going to share my screen. Okay. And I'm going to summarize the conduction abnormalities. Okay. The last time we started to discuss the arrhythmias, and we called arrhythmias that everything else that is not a normal sinus rhythm. And what we specify what the normal sinus rhythm is, basically is rhythmic. The PP intervals is normal. The RR interval is normal. Every P followed by QRS, the PR interval is normal. And the P is originated from this SA node. This is the no, and the rate is between 60 to 100. That's the normal sinus rhythm. And the first we started that we can have arrhythmias when we have an abnormality of the impulse formation. What does it mean? We can have an arrhythmically generated impulse that it doesn't come in time, or it's coming faster or coming slower, or it's not originated from the SA node. So this is why we do have, let's see, as the disorders or impulse formation, such as the heterotopic when it's not from the sinus, and the nomotopic that is going through the sinus, but we have different type of arrhythmias. Now, the next session that we starting today's, or you already watched these videos, when we do have a completely normally formed impulse, that the impulse is formed in the SA node and it comes rhythmically. So everything good with the impulse formation, but that impulse that is formed is not propagated normally to another area of the heart. And this is what is called conduction abnormalities. There are two big portions of the conduction abnormalities. When we do have a slow conduction, or we do have a block of the conduction, or we do have a faster conduction, and this is what is called pre-excitation syndromes. But let's first, let's see, stick to the conduction abnormalities when we do have a slow conduction, or what is called a block. Now, depending on the severity of the block, we grading this severity. The less severe is called grade 1, and the most one is grade 3. What does it mean? Grade 1 means that every impulse that generated gets to another area, but slower. So it's meaning that slowing the conduction. Grade 2 means that the conduction is worsening because there are some unconducted bits. And grade 3, the severe one, there's no connection between these two areas of the heart. This is the third degree block that we have. Depending on the location of this block, anywhere inside the heart where we have some kind of classical connected areas, such as the SA and the atrium, that's the SA block. Between the atrium and the ventricle, that's called the AV block. And we do have the intraventricular blocks. So these are the different types of the conduction abnormalities. Now, when we talk about conduction, we always evaluating the connection between 2 points. I named it A and B. So A is the starting point for the conduction, and this kind of charge gets from A to B. Normally, we do have a certain velocity how the charge gets to A to B, so we have a certain time period when the charge should get from one area to another area. That's a normal. Now, what do we call as a first degree block? First degree block means that we do have a connection between A and B, and every impulse that is originated in A is getting to B. However, this is slower, so it takes longer time to get one point to another one. So if we had, for example, a connection that the speed was, for example, 1 millimeter per second in a normal case, now we do have, for example, 2 or 3 or 4 millimeter or less, half millimeter per second. So about 50% the speed, but every charge gets through from A to B without any kind of any problem. So that's be rhythmic because this conduction always the same, but slower. So it won't cause any arrhythmia because every charge gets from A to B. Now, sorry, what do we call as a second degree block? Second degree block calls that we do have a good connection between A and B. So mostly the charge that's raised in A gets to B. However, there are some unconducted bits. So mostly conducted. So there are more connection than unconduction. So this means second degree. Very important that between two conducted bits, we cannot have more than only one unconducted. If you have more than one unconducted, that's be the high degree block. So that's meaning that only one unconducted bit can be between two conducted one. Now, this be a rhythmic one, because when we have conduction, that can generate, let's see, the ventricular contraction. When we do not have any connection, that we don't have ventricular contraction, so that's be arrhythmic. Depending on the severity of the second degree blocks and the type of this block, we have Mobitz type 1, Mobitz type 2. Mobitz type means that the speed of conduction is gradually worsening, and after we have a drop bit, and again start from the beginning. So it looks like the cycling back and forth. So the conduction is worsening, and after dropping, it's a little rest, and after coming again, normal, slowing, dropped. So this is how it works. So it meaning that we do have a slow conduction, slowing down the conduction. After no conduction, again start from the beginning. So it is faster, slower, no conduction. Faster, slower, no conduction. This is repeatedly coming, and this is called second degree Mobitz type 1. It's Mobitz 2, Mobitz type 1 block or Wenckebach periodicity. There is another type when we have Mobitz type 2 block. Mobitz type 2 block means that we do have a constant speed. So whenever the conduction goes through, the speed the same, it won't slow down, or that doesn't change the conduction, but we do have some unconducted bits. This is what we do have. Okay, that's clear. Now, 2-to-1 blocks. 2-to-1 blocks means that it can have that one conducted, not conducted, one conducted, not conducted, one conducted, not conducted. Now the problem is this is a second degree, still second degree, because between two conducted, we have only one unconducted one, and it can be Mobitz type 1, Mobitz type 2. We cannot differentiate using this 12-lead ECG, but the clinician always put their pacemaker into this heart, so they don't worry too much about it, about this 2-to-1 block, but we do have a separate entity for this kind of block. We do have a high degree blocks. High degree blocks means we do have much more unconducted bits than conducted one. So how can the patient survive this situation when they do have mostly unconduction between two areas? We have to have a lower pacemaker center, and escape rhythm is going to save the life of the patient. So as you see here, no conduction, no conduction, no conduction, some conduction, no conduction. So only one possibility is that some kind of lower center is going to hit, or especially in this area, depending on what grade this unconduction we have. And the worst one, when we have no connection between A and B at all, and for sure, all the time, we do have escape rhythm, a lower center is going to fire. Now, this kind of conduction abnormalities can be anywhere inside the heart, as I mentioned, can be between the SA and the atrium, that's an SA block, or can be between the atrium and the ventricle, this is an AV block, and can be intraventrically inside the ventricle. Okay, the best one to start with the AV blocks. Why? Because we do have the A point, such as atrial activation, we do have a B point, such as the ventricle activation, and we are evaluating the connection between the atrial activity and the ventricle activity. So you can see both when we have the A, when we have the B. No doubt about it, it's very nicely can be seen. Now, another problem with the assay block, that in assay block, we don't have this connect because what is that? There is no sign of A. We don't see on ECG when the sinus node is activated. What we do see on ECG, that's the atrial activation. So we do see only the P wave. There is no sign of the sinus activity. If you have an esophageal ECG, yes, you could see the sign when the assay is activated, or when you do have, for example, an intracardial ECG, yes, you can see it. But in the normal peripheral ECG, you cannot see it. This is why it's more difficult to understand and difficult to diagnose. Intraventricular conduction abnormalities, we do have bundle branches inside, right and the left one, and this can be blocked. And of course, we do have the A and B located inside the ventricle. So what it has, widening of the QRS, and the morphology of the QRS is altered. So only the QRS should be evaluated when we want to see any kind of ventricle, intraventricular conduction abnormality. Now, let's start with the AV blocks. Okay, the AV blocks. AV blocks incomplete when we have third degree, second degree, and high degree. This is the incomplete, and the third degree is a complete one. Let's start with the first degree one. What the first degree means? The first degree means that we do have every P followed by QRS complex, but the PR interval is longer. Okay, so what we do see that rhythmic, the heart beats rhythmically. Every P is originated in the same area, okay, in the same time, in the same area, but the PR is getting longer. When the PR is getting longer, but because the velocity is the same, this is why it's rhythmic. So what we have to look at, from the beginning of the P to the beginning of the QRS, this PR interval is elongated. This is what, but every P followed by QRS, so that's be rhythmic. And you can say that is over 0.2 seconds. Now, the PR interval is not constant. The PR interval depends on the heart rate. If you have faster heart rate, your PR is shorter. If you have slower heart rate, the PR is longer. If you are younger, the PR is shorter. If you are elderly one, the PR is getting longer, but never ever be longer than 0.2 seconds. This is what you can remember, okay? Now, this is how it looks like. Rhythmic, yes. Heart rate, 1, 2, 3, 4, 4.5, for example. It's about 60, 65 or 70, that's okay. Do we have P wave? Yes, we do have P wave, and the P comes rhythmically, but the PR interval is longer than 0.2 seconds. This is 0.2 seconds. So this is why that's a first degree AV block. Good. This is very similarly, this picture, I think we do have this picture in the case studies as well. Okay. Second degree AV block, what we said, this is when the P wave comes regularly, but some P is not followed by QRS. And it looks like the RR intervals won't be the same. For sure, when the P is not followed by QRS, it won't be the same. There are two types, MOBIS type 1, MOBIS type 2. Let's look at first MOBIS type 1. When we have MOBIS type 1, it's meaning that the impulse conduction through the AV junction is worsening. So it's getting longer, longer, longer. Once is not conducted, the P is not followed by QRS. So when you look at the PR interval, is getting longer, 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 not conducted, start from the beginning, normal, longer, longer, not conducted. So this is one thing. And that's very easy. But the P intervals are constant. But here, there is a drop, it is not followed by QRS. So that is for sure is arrhythmic one. That's very easy to understand Mobitz type 1 or diagnose Mobitz type 1 because you see the PPP. You can put a paper and mark it where your PPs are. And after, when you see that, this is a not conducted P wave, look at the last one and compare the last PR to the first PR. And when you do see the last one is longer than the first one, that's Mobitz type 1. Now, another thing that we have to look at, the RR interval is not, you don't need it for diagnosing AV block, Mobitz type 1. But it's good to understand because if you want to diagnose SA block, only one thing is left, the P waves and the changes of the PP interval. That can be a clue, whatever is a Mobitz type 1 or Mobitz type 2 SA block. We will get on later on a little bit. If you look at the RRs here, it looks like a little bit getting shorter. And I will explain you later why. So this is the Mobitz type 1 block. P, P, P coming regularly, but this P is not followed by QRS. The RR intervals getting shorter. And when you do have these drop Ps, these RRs is less than twice as the last RR. This is what Mobitz type 1 block means. So, diagnosing last conducted PR longer than the first conducted PR. Plus, you can use that this interval when the drop P has is less than twice as the last RR interval.
Can I ask a question?
Yes.
So this is a sinus rhythm? Or yes. Not, because there is no.
It's a sinus. That's a sinus rhythm.
Even though we don't have a QRS after the P.
Yes, but this is not a normal sinus rhythm. Sinus rhythm only means that the sinus generates the impulse and activates the atrium.
So it's a sinus rhythm, but it's a normal one.
Yes. Yes.
Okay.
Yes. Yes. Now, so this is the explanation. If you go through and look through the whatever the written stuff that you can download from the YouTube, you will understand that these RR intervals are getting a little bit shorter because this elongation relatively, it's, as you see here, the PR elongation somehow is shortening the TP interval here and less, and this is why the RR interval is getting shorter one. Simple. Arrhythmic? Yes, it's arrhythmic. When we do have an arrhythmia, how do we calculate the heart rate? We count a longer interval, meaning 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. How many are we have? 1, 2, 3, 4, 5, 6. So the rate is 60 per minute. Okay. Do we have P wave? Yeah, we do. The PP intervals are constant. This P is not followed by QRS. Let's look at the last conducted PR and compare to the first one. This is longer than this one, so this is why it's Mobitz type 1 second degree AV block. Axis 1 is positive, AVF is equiphasic, okay. AVF is 90, perpendicular is lead number 1, it's 0 degrees, so it's the horizontal axis. Fine. Next one, Mobitz type 2. Mobitz type 2 means that's a distal one. So it's meaning that why Mobitz type 1 include the AV node as a proximal block, mostly reversible block. So it's very low the chance that develop the patient a third degree AV block. However, in Mobitz type 2, yes, there's a ischemic changes and usually progress to third degree AV block, and only the ventricle escape rhythm can save the life of the patient. So that's with a very low cardiac output. This is why they put a pacemaker. This is why it's important to distinguish Mobitz type 2 and Mobitz type 1. What it says, PP comes regularly, but we do see a P that's not followed by QRS complex. If you look at every P followed by QRS, except here, if you compare this distance, this R is exactly twice as the last RR. This is how you can distinguish compared to the last PR to the first one, they equal. There's no changes, and the RR intervals is the same, and this drop one twice as much as the last one. This is how you recognize it. 2 to 1, we have rhythmically coming P's, and every second P is dropped or every second B is conducted. This is how you can see very slow the heart rate because half is a normal one. So we do have a sinus written. If you look at the rate of the sinus, is about 1, 2, 3, 4, 75. Why the ventricle half the 75, 30, for example, the exit 32 that we do have here. That's simple. Here as well. Okay. Look at the high degree, what it means. Mostly unconducted, but sometimes conducted. Okay, when it's mostly unconducted, what does it mean? If it's not conducted, not conducted, not conducted, only the ventricle escape rhythm can save the life of the patient. So we do have a ventricle escape rhythm. Whenever the impulse goes through, we do have a P followed by QRS complex. So here, and this QRS be narrow, it looks like a supraventricular bit. So that is called the capture bit. But and this is not in time, so that makes it arrhythmic. So the high degree AV block is arrhythmic. When we do have an escape rhythm, that's rhythmic. But when we have a capture bit, that makes it arrhythmic. Now, there's a chance that the ventricle is sometimes activated simultaneously from the escape center and the supraventricular conduction, and this is why we do have a fusion bit. So it means that from the atrium, the charge comes, plus from the ectopic center, and both activates the same time the ventricle. For sure, this comes in time. So the RR as an escape rhythm is the same as a RR fusion. But the RR capture is different from the RR or an RR fusion. This is how you can distinguish between these two. So we do have 3 types of morphology of the QRS complex. We do have one, the ventricle escape. We do have a fusion, and we do have a supraventricular picture bit. Okay, this is what we have. Okay, third degree block, meaning there is no connection between the P wave and the QRS complex. How can we see it? If you find a PP interval, you can mark a paper and shift it, and you will see some P's that inside the QRS or inside the T or inside the ST segment. And if you have a ventricle rhythm, that's be easy because the QRS is wide, the T is inverted. But if you have a junctional one, only what you see, narrow QRS, positive T wave, but you do see some P's inside the QRSs. This is how you see that there's no connection between P and QRS. One thing, very easy one, if you count the rate of the P, is not proportional to the rate of the QRS complexes. And this is that there's no connection between the P and the QRS complexes. So third degree block associate usually with an escape rhythm with a lower center. And this is what is called AV dissociation. Okay, this is very nicely. You can see that we do have a zillions of P waves, for example, and the QRS is very slow one. And look at the PR distance. The PR distance is changing, and there is no longer, and not conducted, but sometimes short one, sometimes and longer, getting longer. So it's not connected at all. And if you count the rate of the PPP, it won't be proportional to the rate of the ventricle rate. Okay, this is third. That's a ventricle rhythm, what we have here. Okay. Now, let's go to the SA blocks. The SA blocks means that we do have an SA node that generates the impulse. However, the surrounding area, it doesn't let the charge goes through. So this way, the atrium, when we have a third degree, is not activated at all. So it's meaning there is no P wave. This is what we are talking about, the third degree. However, when we do have a first degree, it's meaning that the charge goes through to insulated area, but slower. So every impulse generated by the ST generates a P wave. So we cannot diagnose based on this normal 12-lead ECG. Not at all, because what we see only the P wave, nothing else. So if you had an esophageal ECG, you can compare the sinus activation and the time between sinus activation and the P wave. But using 12-lead ECG, no. So this is out. Second degree, now that's a problem because we don't see the sign of an SA. We do see the sign only when the atrium is activated. So looks like when we do have an AV, only we have the QRS complex. So we have to evaluate the PPPs. When we have a block, there is no P. Okay, there's no P at all. Now, how can we distinguish whether it's Mobitz type 1 or Mobitz type 2? Let's look at the P's. Okay. Now, for example, let's start here. Sinus is starting, and after you have the atrial activation, and this is the conduction. As you see here, it's getting longer. And when we have no connection, when we have a drop one, as you see here, these PP interval, when we have the drop P's, it's relatively shorter than twice as this one. This is how you diagnose a first degree SA block Mobitz type 1. Okay, so the P is missing. In AV block, P was present, but there is no QRS. Here, no P wave, and this is why it's no QRS. So let's look at, this is a normal one, and that's the SA block. Relatively, P, there's no P. Okay, PP, and look at this PP last. That's B taking twice less B as this is here to twice the distance. Okay, so it's very similar to the RR. So this distance B a little bit shorter than this distance. That only means the Mobitz type 1 SA block, no P wave, no P wave. Mobitz type 2, exactly the same as the twice as the PP interval. That's it.
So I have a question.
Yes.
If I want to differentiate between SA block Mobitz 1, for example, and AV block Mobitz 1, so I'm looking for a P wave. And if I have a P wave, so it's AV, but no QRS, so it's AV. And if I don't have P wave and no QRS, so it's SA block.
Yes, correct.
Okay, thank you.
Correct. For example, here, what we have here, relatively, well, that's a T wave, it's not a P wave. Here, there is no P wave at all. We do have PPP. And if you can't, let's see the P's, for example, you can see the PPP is no P. And when you take twice as, this will be shorter one. This is how you know that SA block, Mobitz type 1. Mobitz type 2, again, PP, no QRS, and twice as exactly and this distance. So that's distance taking twice, that's be the same. This is why SA block Mobitz type 2. Okay, simple. Now, we got into the ventricle. In the ventricle, we do have branches, bundle branches. We do have a right side as a right bundle branch, and on the left side, we do have an anterior fascicle, the septal, and the posterior fascicle branches. Now, these branches can be blocked, and if we block the branches, relatively that area of the ventricle activated slower from the other part, whatever is activated normally. This is how we distinguish right bundle branch block and left bundle branch block, and we can distinguish an anterior hemiblock, such as the anterior fascicle conduction abnormality or the posterior fascicle abnormality. This is how we can have. There are some bifascicular blocks, such as when we have a right bundle branch block and one of them, a hemiblock, is missing. These are the bifascicular block. And if you do have a bifascicular block plus an AV block, these are called the trifascicular blocks. This is how we can distinguish. And of course, usually these blocks is due to ischemia or myocardial MI. Let's revise what the normal ventricle activation looks like. First, the septum is activated. The septum activated from the left bundle, about 90% of the cases from the left bundles. And this is why In V1, we do have a positive deflection, and in V6, we have a negative one. And after the ventricle activation, right and left simultaneously, left is thicker, electric activity higher. This is why we do have a positivity on the left side and negativity in the right side. So here we have an RS, here we have a QR complex. Now, you learn in physiology that the ventricle activation time or the intrinsicoid deflection is from the beginning of the QRS complex till the last R wave, and that's different on the right side and the left side. On the right side, that's be about less than 0.0 second, and the left side is less than 0.06 second. So that's be different because that's far further from the ventricle activation. That's the normal situation. If we have a block on the right side, the ventricle activation time be longer on the right side. If we have a problem on the left side, that ventricle activation be longer on the left side and doesn't change on the right side. Let's look at right bundle branch block. Septal activation, normal. There is no changes at the beginning. Ventricle activation, left side activated normally, normal. However, right ventricle can be activated only from the left side, meaning that, again, we do have an R wave in V1 because the activation goes toward the V1. So this is an RSR complex. And as you see here, the last part of the QRS is elongated. And we do have a negative wide S wave on the left side. So that's, again, a wide S wave on the left side. If you look at the ID time, is elongated on the right side, doesn't change on the left side. This is how you know that that's a right bundle branch block. But you're always looking in V1, the RSR complex and the wide S wave on the left side. Okay, good. Let's.
Professor?
Yes?
Can you explain about why in the V1 R is started and in the V6 Q is started?
Which one that you're talking about?
Yeah, here. Yeah.
Okay.
In the V1 R is started
Okay.
first.
Because that's the septal activation. The septum is activated from the left bundle. The left bundle is intact. And this goes from left to the right. This is why you do have a positivity in V1 and negativity in V6, because it goes away from the left, goes toward the right.
So it is only related to the direction of the vector?
Yes, that's it. That's it.
Okay.
Exactly. And the next one, when the ventricle is activated, but left one activated. So it goes from the right to the left, because the left side is activated. This is why you have a negativity in V1 and positivity in V6 or left side. And when you do have, again, an activation of the right side, it goes from the left to the right. And this is why you have a positivity in V1 and negativity in V6. Yes?
Okay, I got it.
Okay, good. Let's move on. Here, very similarly, this is what you decided. Okay, this rhythmic, fine. The rate is around 70, maybe a little bit more, 80. Okay, we have P wave. Yes, we do have a regularly coming P wave. PR is normal, X is, but it's about normal. AVF, it's about normal, but 90 degrees or so, very close to 90 degrees, because that looks like epiphasic. Okay, QRS is wide. Yes, it's wide. It's very important because it's meaning that the intraventricular activation takes longer time. Okay, good. Have to look at V1 and V6. Where do you see this R complex? V1. So right bundle branch block. That's it. Okay. Now, incomplete and complete doesn't matter, both showing the same kind of characteristic sign. So the M complex or the S wave, but the duration of the QRS, if it's less than 12, that means incomplete. If it's more than 12, complete. That's it. Nothing else. I'm sorry. Let's see the left bundle branch block. Left bundle branch block, we have a problem with the septal activation because the septal bunch is missing. So only this area can be activated from the right. So we have a vector that goes from right to the left, This is why, okay, what we have? We do have a negativity starting in V1 and positivity in V6 because the vector pointing toward the left side. After which ventricle is activated? The right one, because the bundle is there. Again, we do have a little positivity here, but because the left is starting right away with the septum, we do have a more negativity and we do have a positivity in V6. So as you see here, you can look at what's happening. Here we have a QS complex or W, and here we have an M complex in V6, where the ID time is elongated on the left side. So you know that the ventricle activation takes longer on the left side. So if you want to find the wide R complex, is located on the left side. Okay, good. All right, this is how it looks like. Rhythmic, fine. Now here, PR interval, it's okay. It's about the borderline. Axis, one positive, negative. It's about 0 to minus 30 because that's a little bit positive. QRS is wide. Yes, where do we see this wide R wave? It's V6 on the left side and lead number 1 and QS complex in V1. So that's a complete left bundle branch block. Good. Now, because the left bundle composed of two branches, the anterior fascicles and the posterior fascicles, and both separately can be blocked, we can have an anterior fascicle conduction abnormalities or a posterior fascicle and conduction abnormalities. Very simple. The duration of the QRS is not altered, only the axis be altered. Now, if you put your arm some here, if you grab your child, for example, that's an infant one. Usually the head is close to your heart, okay? So your left arm is above and the right one below. And this is the normal activation. If the anterior is missing, that's an anterior when your left arm is missing. So only from the posterior can be activated this area. So you have a pathologic left deviation. If the posterior fascicle is missing, you have a pathological right deviation. So it goes toward the right side. This is how you can distinguish. So the method of the axis, this is how you diagnose the hemiblocks. Rhythmic, sinus, rate, 1, 2, 3, 4. It's about, let's see, for example, 65, good, P wave, yes, PR, normal, QRS, well, it's a borderline 0.1 second, good, axis 1 positive, AVF negative, lead number 2 negative, extreme left deviation. So that's a left anterior hemiblock. It's not rhythmic right here. We do have a, as you see here, right away, you can see we do have an atrial premature contraction here, right here. Because we have a P wave here. We don't see the P wave right here, but here I do see the P wave. Okay, good. Posterior, the opposite. When the axis exactly on the other side, we do have an extreme right deviation. Yes, rhythmic, yeah, rate is around 100. P wave, yes, sinus tachycardia, okay. PR is okay, normal. Axis, negative. AVR is negative, but you can say that's the extreme right deviation, good. QRS is narrow. Okay, what thing you can diagnose? That's a posterior hemiblock. That's it. Now, bifascicular blocks, as I mentioned, when we have a right bundle branch block, the typical sign of a right bundle branch block, such as an M complex in V1 and a deep SV1 lead number 1 or 6, okay, somewhere here, yes. And we do have an axis deviation, an extreme left deviation, 1 positive, 2 negative. That's an anterior hemiblock. Or we can have the opposite one when we have a posterior hemiblock, when we do have a, but this is not a posterior hemiblock for sure, because that's an anterior. So it's normal. That's an axis is completely normal. That's picture is not normal. I think it's not normal. I think there's the old version of the PPT5. Okay. Now, trifascicular block. What the trifascicular block means? Trifascicular block means that do have a bifascicular block, right bundle branch block, and the hemiblock. Plus, we do have a first degree AV block. So the PR interval is elongated. Or we do have a left bundle branch block and the first degree AV block. That's again a trifascicular block. Okay, good. That's it. Go on. This block can be rate dependent. If the rate increases, less time for repolarization, and it's meaning that this is not a complete third degree block, that's a high degree block. When above a certain rate, you see the right bundle branch block, and below a rate, you don't see the right bundle branch block. So this is the frequency depending intraventricular conduction abnormalities. So far, we had those things when we had a slower conduction. We can have faster conduction, and this is what is called pre-excitation syndrome. Usually, we have an accessory bundles, such as between the atrium and the ventricle, that's a bundle of Kent, or between the atrium and this goes to the James fiber goes to the bundle of His. So these are the WPW syndrome, and that's the LGS syndrome. Okay. Most common one, the WPW syndrome. Usually we do have a bundle of Kent that connecting the atrial muscle to the ventricular muscle. What is the problem? The problem is that when we have the charge in the atrium, it activates the atrium, fine. Reaching the AV node, okay. Reaching the bundle of Kent, fine. What will happen? After, when it's finishing the atrial activation, the bundle activation starting right away. And when the AV junctional delay reaching this activation, it will activate the left over part of the ventricle. So this is why the slow starting and fast ending QRS complex you see, and this is what is called the delta wave. That's a delta wave. Okay, this is what it's called delta wave. So the PR is short and the QR is wide. There are two types of this WPW syndrome, major types. The A, when in V1 we have a positivity, or B, when we have a negativity. Is depending on where this bundle of Kent is located. If it's located on the left side, we have a A. If it's located on the right side, that's a B type. That's it. Okay, that's an A type, as you see here, is starting positively. Okay, or it's a negative, that's a B type, and you do see this nice delta wave and short PR interval. LGS syndrome, PR is short, QRS is narrow, so it's nothing else. Only what you do see that P followed right away with the QRS complexes. That's it, nothing else.
Professor?
No. Yes?
For the Wolff-Parkinson-White syndrome, the P wave can be overlap with the QRS.
No.
No?
The P should be in front of the QRS complex. It's never inside the QRS complex, but it's close to the QRS complex. Okay, that's very important. If you look at this, immediately after the P, QRS starting. This is how you diagnose it. So never ever be the P inside the QRS complex. Okay. Now, because we do have two parallel pathways, that's a chance that we have a re-entry cycle. Because two parallel pathways with different refractor period, different refractor period or different velocity, that's a chance that we do have this re-entry cycle. Now, there are two possibilities. One possibility is when the ventricle activated through the normal conducting system and the bundle of Kent reuptakes the charge. This is one circle of the re-entry. Okay. But all the time, the ventricle activated through the normal conducting system, so that's been narrow, but fast. And when we do have the opposite direction, bundle of Kent activates the ventricle, AV junction reuptakes the charge. We do have a wide QRS complex, tachycardic one, that's an antidromic, and orthodromic AV-RT tachycardias. These are the two types of both supraventricular but macro re-entry that we have. The patient can stop it by carotid massage, so altering the AV conduction, and that can cut, let's see, the circle, this re-entry circle or cycle, and immediately that be normal. This is how it looks like. That's an antidromic, because it looks like it's a ventricular tachycardia, but you know that in the rest, the patient has a the delta wave, and the patient suffering of the WPW. So you can assume that this patient has not a ventricular tachycardia, but a WPW syndrome. And if the tachycardia can be seized by carotid massage, for sure is a supraventricular tachycardia, is not a ventricle, because ventricle cannot alter. Okay, orthodromic one, narrow QRS, and of course at rest the patient has the delta wave. This is how you know that it's not a AV-NRT tachycardia, because AV-NRT tachycardia looks the same. What is AV-NRT tachycardia? When there is no accessory pathways, only inside the AV node we have this re-entry cycle, and narrow QRS that we detect. That's the most common cause of a supraventricular paroxysmal tachycardia. That's an AV-RT tachycardia, AV-NRT tachycardia, identical. So at rest, the patient does not have any kind of delta wave, any kind of PR shortening. Okay, so that's the theory that we had. And now let's start the what we have, the pictures and the homework, whoever had the homework, and I will show it, okay? And only I wanted to find, but okay, good. All right. Okay, wait a minute, I have to share the ECG tracing, okay, material tracing, and that's the conduction abnormality, okay. 101, that's the first one, okay. I share my screen, and I don't know who has this 101. Anybody can recognize this? I can find it, who had it, okay. EKG, okay, group 10, and that's be the third homework, okay. Of course, the names are changing, so this is why it's difficult to start. And yes, I think Rania is not here, okay, great. Yeah, she left this group. So the first one, Maximilian.
Hello.
Okay, so you have the 102, yes? You have the 102. Okay, good. But okay, let's see, 102. I somehow have to move this away. Okay, 102. Let's be identical with 101, so it's a not big deal. Okay, let's start to evaluate this ECG, please.
Okay, so we see it's rhythmic.
Mm-hmm.
We can calculate the heartbeat. It's about 4 large and 4 small, which is about 62 beats per minute.
Okay.
If we want to see the axis of the heart, we can see the third lead is the most equiphasic.
Mm-hmm.
And which would mean we have to look at the AVR, which is negative, which then is plus 30 degree.
Correct.
And then we look closer and we can see the P wave, the QRS, everything. But if we take the time of the PR interval, it's about 9 millimeters, which we can then divide by 25, which gives us a length of 0.36, which is very long.
Yeah. Yes, exactly. Okay.
We have a atrioventricular block, and we can see
that's a first degree AV block. Okay, first degree because rhythmic and
every time.
Yes. Okay, every time goes through. Next, the width of the QRS is narrow, so there is no intraventricular conduction abnormalities, no excessive deviation, so you can conclude that's it. Okay, it's a first degree AV block. All right. It was clear, everybody? Okay, I think the next one is June.
Yes, I'm here.
Okay, it's yours.
Okay, so first I calculated the beats, and since it seems to be arrhythmic, I use I counted how many art peaks there were in 5 seconds, and I found that there were 60 beats per minute. So that's like
That's good.
in the
Correct.
normal.
Okay.
And as I previously said, it seems arrhythmic. So I checked the P wave, and
Okay.
since the P wave is positive in lead 2 and negative in AVR, it was proven to be sinus P wave, so sinus
Correct.
arrhythmia.
Okay.
As for the axis, lead 1 is positive, and AVF is also positive, so it is within the normal range of 0 to 90 degrees. And then I looked at lead 2 specifically, where like at the bottom of the rhythm strip, and I could see that there are always P waves, but there are some QRS complexes that are not accompanied by P waves, and so that would be the second degrees Mobitz 1. And the reason why I concluded to be Mobitz 1, type 1, it was because the PR interval becomes longer, and then you
No, the last conducted PR is longer than the first conducted. It's okay. Here you can see that the second one is longer than the first one, the third one is longer than the second one. But sometimes if you do have a lower conduction, relatively, it's very difficult to see the elongation. Here you can count that 1, 2, 3, 4, 5. So 5 to 4 conduction occurs here, because we have 5 beats P's and only 4 QRS complex. So 5 to 4, the conduction ratio. Okay.
Okay, so just for clarification, when you try to decide whether it's Mobitz type 1 or type 2, you better use the length of the twice of the RR of the last.
No. I said this is a drop P. Okay. Look at the last PR and compare to the first one. If they are not equal, the last one is longer than the first, you say that's Mobitz type 1. If they are equal, Mobitz type 2. That's it.
Okay.
All right. Good. The next one, I think 104.
Yes, it's me.
Okay.
Yes, so looking at the lead 2, we can see that it's arrhythmic. And so I used the 10-second rule. I counted 7 peaks in about 6 seconds. So multiplied by 10, it's about 70 beats per minute.
Okay.
And the lead 1 is positive and AVF is also positive. So the axis is a normal axis. But in lead 2, there's a dropped beat. And before it, the last conducted PR interval is longer than the first conducted PR interval. So I concluded that it was a second degree AV block, Mobitz type 1.
Correct. What is axis?
Sorry, what?
Axis. Have you calculated axis? Maybe I forgot about it, but I didn't hear it.
Oh, I said it's in the normal axis.
Okay, that's good. Okay.
Yeah.
Okay, and the QRS is narrow, so there's no intervention conduction and normality. Good, very good. Thank you. Okay. All right, now that's a good one. Who has this 105? Nobody. Okay.
Oh no, I think the person. You should check your chat.
Oh, again, no microphone. Oh, again, there's no microphone in there. Okay, the heart rate. Okay, it's arrhythmic. Okay, that's great. Okay, I'm reading it. The heart rate is around 60. That's okay. Okay, we don't need the ST aggregation. First, we have to see that is arrhythmic. Okay, heart rate is around 60. We do have, let's see, P waves comes regularly, but the P wave, okay, now let's see this PP interval. Okay, it's written that second degree Mobitz type 1. I don't think so, because that's a drop one. See, that's a drop one. And let's compare the last conducted PR to the first one. And this is equal. So that's Mobitz type 2, not 1, Mobitz type 2. And doesn't matter how long the PR interval, it's only meaning there is no changes in the PR. Okay, that's good. Now, here we have another problem here. Look at here. This looks like we have, let's see, about equally placed RR. Okay, but here we have something else. What do we have here? We have a early coming bit. So that's a, because we have a P wave, but that P wave is different from the previous one. I think an atrial premature bit is right here. This is what it was written here, but let's see a little bit more closely. Okay, let's see a little bit more closely. First of all, it looks like the RR is equal. Yes, up to this point. Here is not, but here everything is fine. Let's look at the PP interval. The PP interval, I would say that somehow maybe here we do have a PP interval, and I think we do have a P wave right here. You can see a little notch. So I would prefer, is not a Mobius type 2, but I think it's a 2-to-1 AV block, 2-to-1 AV block. So have two P waves, and one conducted, the other is not. One conducted, other is not. So this is what I would say that's a 2-to-1 AV conduction abnormalities. Now, the QRS is narrow, is okay. The axis is fine, it was fine. And it's okay that the ST elevation, but the ST elevation comes in the next seminar when we do have the ischemic heart diseases. So let's stick to this one. So that's, I think it's a 2-to-1 AV conduction abnormality. All right. Okay, let's move to 106. Oh, that's a tricky one. 106.
That's mine.
Okay, no, that's a difficult one.
Yeah,
I think so.
I didn't sleep yesterday because of. So the what? The angle? Since
At the first, it's rhythmic or not. This is the first one.
okay. Sorry, it's not really rhythmic or
No, it's not rhythmic. It's not rhythmic.
Yeah.
It's not rhythmic. You can say that it's not rhythmic. Okay, good.
Mhm.
Heart rate?
Heart rate is like average is like maybe a bit less than 100, let's say 90.
Yes, it's okay, 90. That's fine. That's 90, but
So
it's
it's
not
normal.
rhythmic. Okay. Axis?
Axis, the AVF is like equivasic,
Mm-hmm.
and the one perpendicular to it is lead one, and lead one is positive, so it should be 0 degree.
Mm-hmm. Good. Now, the worst part of it. If you get closer, you can see that there are some very weird bit. Looks like spike.
Is that P?
There, no,
relation?
it's a spike. It's a no, that's a spike. That's a spike. That's an atrial pacemaker. Atrial pacemaker. Okay, that's the problem. Okay, and what is another problem? Not only that we do have a spike, see, we do have a spike, and looks like
there's no really P wave.
Yeah, there is no P wave, but looks like the spike and the QRS is getting further from each other. And once there is no QRS after the spike. So we do have an atrial pacemaker with a Mobius type 1 AV block.
So it's the patient with Mobius type 1 AV block, and he has a pacemaker. That's why we see the spike.
Yes, that's it. So when we do have the spike, if you do have a spike in the QRS, that's a ventricular pacemaker. If you have in the P wave or close to the P, that's an atrial pacemaker. I do have a separate videos about the pacemakers. I think, I don't know, maybe in a ischemic heart disease or somewhere there, I don't know exactly. I will show you, and you can revise these pacemakers as well. But that's a tricky ECG. I can say it to you. That's a tricky one, but you did it very nice. Okay, 107. Who has this 107?
Yeah, that's me.
Okay.
So it's regular, slow ventricular rate around 40. The axis should be around minus 30 degrees.
Yes.
We can see 2 P waves per 1 QRS, so I would say 2 to 1 AV block.
Yes, that's it. 2 to 1 AV block. Okay. Axis is what was axis? And again, overslept again.
Around minus 30.
Yes, I know, minus 30, between 0 and minus 30. Okay. Now, another thing that I haven't mentioned yet, you should look at the morphology of the P wave, and you see that the P is elongated and nudged.
Yeah, that looks like a left atrial enlargement.
Correct. Yeah, you know everything. Yes, that looks like as a left atrial enlargement. Very good. Congratulations. Very, very good. Good. So that's a 2 to 1. Okay, good. All right. 108. Ooh, look at this. 108. Who
Okay,
has
so
the
it's
108?
mine.
Okay.
So this is rhythmic, and heart rate is, there are 9 boxes between all intervals, so it's around 30 BPM.
Okay, good.
For 33, so it's bradycardia. And for the axis, the lead one is positive, and also AVF is also positive. So
No. AVF is negative. AVF is negative, and the 2 is negative. Okay. So that's an extreme left deviation. That's an extreme left deviation. Okay.
Okay, and also on, I guess, in many P waves here.
Yeah, too many. Yes.
So yes, so it can be 3 to 1.
No,
AV.
we have a P wave right here as well inside the T. Okay, so we have
this one
1,
is also
2, 3, 4, and out of 4 we have only 1 QRS, so that's a 4
So
to
4
1
to 1.
conduction. Okay, and we do have an extreme left deviation, and is the QRS is wide. I would say yes. Okay.
Yes, yes.
Okay, and in V1 you see this RSR complex, see? Okay, so what does it mean when we do have an RSR complex in V1 and the deep S wave on the left side? That's a right bundle branch block. Okay. That's another normal one. And this is, as you see here, the last part of the QRS is wider. So this is why that's a right bundle branch block plus left anterior hemiblock. That's a bifascicular block and a 4 to 1 AV block. That's a high degree AV block. Okay. So everything should be considered when you want to make this diagnosis. Okay, go on. Next one. Ooh, that's a good one.
Okay. So it looks rhythmic. And when I calculated the beats, I got around 50 beats per minute. So it's bradycardiac. And it has a normal axis. Yeah. And we see that every second P wave is conducted. So I think it's going to be a 2 to 1 AV block.
No. This is lead number 2 all the way, 2, 2, 2 all the way. Now look at the PRs. Okay, it looks like okay, but here, oh, look at here, they are not. So it looks like there is no connection between P and QRS. Okay, so that means if it's no connection between P and QRS, that meaning that we have a
probably second degree.
No. In second degree is arrhythmic, and this is rhythmic.
Okay. Okay, if there's no connection, I believe it's going to be
Exactly,
a third
that's
degree.
me, third degree. Exactly, that's a third degree AV block. And what is the impulse formation center here?
I don't know.
The junctional escape rhythm. Huh?
Junctional escape. Yes.
Because the
exactly.
QRS is narrow, that's okay. The T is positive, so that's a junctional escape rhythm. Okay. Next one. Ooh,
Yes.
110.
I think it's rhythmic, and
Okay.
the heart rate is around 40 beats per minute.
Good.
And here I saw there is P waves and also QRS, but they're not correlated to each other. So I think
Good.
it's in a third degree or complete AV block.
Okay. And
about the axis, I couldn't really understand if it's normal axis because lead one is positive and AVF is positive.
so it's normal. Okay, that's
So
normal. Yes. What is the impulse formation center? So what regulates the heart? So what generates the impulse? Because you said third degree AV block.
Yes, so we have impulse from the SA node.
No, SA node. Yes, we have an SA node, but you said it's third degree AV block. So there's no connection between the ventricle and SA. So that's a junctional escape rhythm. Okay.
Yes.
You said very nicely, we have a third degree AV block. We do have P waves, but independent from the QRS complex. And you said very nicely that that's the rate around 40. Good, very good. And you said that the QRS is narrow. Fine, the QRS is narrow, but this ST elevation, again, we will learn later on. That's a ST elevation myocardial MI. Okay. And what can it be? That has to be a junctional escape rhythm. It cannot be a ventricular one because if you had a ventricular rhythm, you cannot diagnose any kind of MI, but that's an MI.
Sorry, how about lead one? Is it a little like not that short?
What do you mean?
Like
small?
No, I mean it's a little bit wider, no?
Yeah, it can be wider, but it's only 2 millimeters in width.
Okay.
It's not too wide. It's 2 millimeters is all right. Yeah, it's okay.
Thank you.
No, 111. Who has
Okay,
this?
this is mine.
Okay.
Okay, so it's rhythmic, and the heart rate is 75 BPM. And but the PR, that's the PR interval is longer. It's open right here. So it looks like a first degree AV block.
Okay, go on.
Okay, the axis is so AVL is equiphasic, so it's going to be 60. So the second lead is positive, so it's 60.
Okay, great. 60 degrees. Okay.
Yeah. And if we use the quadrant version, then it's going to be the lead one and AVF are both positive, so it's within
normal.
axis.
Okay.
Yes.
Now, what about the QRS? Width of the QRS?
Without.
Width. How wide the QRS is?
Why?
Wide.
Oh, how wide? Oh, sorry. It's narrow.
Well, 1, 2, 3, almost 3.5, 4 millimeters. So that's wide.
Oh, okay.
It's at least 0.12 millimeters. So that's QRS is wide. So we have an intraventricular conduction abnormality. You have to look at the left side. Left side can be lead number 2 and V1. V1, you have this deep S wave, all the way, deep S wave. And here we have this RSR complex, the M complex, or a nudged R wave in lead number 2 and in lead number 1 and AVL, see? So that's a left bundle branch block, okay? Plus, we do have an elongation of the PR interval. So that's a left bundle branch block plus the first degree of AV block. That means a trifascicular block.
Okay.
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 Okay, that's everything should be considered here. All right. Now let's see who has this. 112.
Me?
Okay.
Can you say about 111 again? So AV block, the first degree and AV block and left bundle branch, and then left hemi block.
No. We only have a first degree AV block. You can see it. Plus, we have a left bundle branch block. Left bundle branch block means that both anterior and posterior missing. So at least 2 fascicle is missing when we talk about left bundle branch block. And the third one is the AV block. This is why it's trifascicular block. So the AV is one and another anterior posterior. Or if we have a right bundle branch block or anterior and posterior and first degree AV block. This is the trifascicular block.
Okay.
Okay. Revise the theory and you will find this information. Okay, let's see this 12. And it's your turn,
So it is rhythmic. And heart rate is about 33. It's bradycardia and axis the right deviation.
Yes, pathological right deviation. Okay.
So 9 to 110.
It's more because if you see that the lead number 1 is negative, AVR is equiphasic. Almost. Okay, so that's 120. Okay.
Okay. And this is sinus rhythm. And the QRS is wide.
Before we do the sinus rhythm. P, 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 P. So it's 1, 2, 3 QRS. 1, 2, 3 QRS. 1, 2, 3 QRS.
3 to 1 AV block.
Exactly. So the high degree AV block, and now you can get to the QRS complex that is wide. Okay.
And so there is a slurred S.
Okay, on the left side. Okay.
So
and in V1, yes.
Is it so right branch?
Yes,
right
bundle branch block plus a pathological right deviation means bifascicular block.
So there is not anterior hemi block.
That's a posterior, not an anterior. Because if you had an anterior, you should have a extreme left deviation, not right deviation, extreme left deviation. Okay.
So it is only bifascicular, not trifascicular?
No, because trifascicular include the first degree AV block, and that's a high degree AV block. Okay, so by definition, it doesn't include the trifascicular, but okay. All right. 13?
Yes, this is mine. Okay, so first I see it's a arrhythmic, heart rate. I counted 6 seconds with 7 peaks, 7R, so about 70. For the axis, I see lead number 2 is equiphasic. So the perpendicular to that is AVL, so around negative minus 30 degrees, but still in the normal axis. Okay, then I can see the P waves, but I feel it's not correlated with the QRS.
Why? Why?
Because I see a P wave and then QRS and then
No,
P
no,
wave
look.
and
P, no QRS. P, QRS, P, QRS, P, QRS, P, no QRS, P, QRS, P, QRS, P, QRS, P, QRS. This maybe the P is here, you can see it, but no QRS.
So maybe it will be AV block second degree, but
Yes.
type 2, Mobitz type 2.
Yes, Mobitz type 2. That's it, Mobitz type 2.
Oh,
Okay. Yeah. And width of the QRS is narrow, so there is no other. Okay. If you assume that that's a minus, but it's a little bit more positive than negative, so I don't think that is the heavy block that you do have here. Okay, good. 14.
It's me.
Mm-hmm.
It's rhythmic, and the heart rate is about 37 beats per minute. And it's a 2-to-1 AV block.
2-to-1 AV block. That's it. Nothing else you can say. Yeah, 2-to-1 AV block. Yeah. Okay, good. And the axis is, well, maybe it's around a little bit negative. So I think it's about between 90 and 100. So that's a right deviation, but not too much. Okay, good. 115.
I think this is mine.
Okay.
So the axis is normal, and the heart rate is a little bit less than 60 beats per minute. And what I see P waves, but like sometimes it's part of the T wave, like A2 on the bottom. But I also find that like if you take 4 P waves together and then the next 4, they match each other, so it's kind of rhythmic that way.
Okay.
Makes sense. And then there's a dropped beat. There is a P wave without a QRS, so it's maybe I forget if it's like 3-to-1 or 1-to-3.
No, you said 1, 2, 3, and 4, and out of the 4 we have 3 conducted, 4-to-3 conduction.
4-to-3. Okay, yes.
4-to-3. And this is what kind of block? What kind of AV block?
Well, it's second degree.
Last conducted, yes, second degree, and the last conducted is longer than the first one.
So it's Mobitz 1.
Mobitz type 1. Okay, good. Very good. Very good. And the QRS is narrow, no intraventricular conduction abnormalities. 116. Anybody has 116? I'll check it. Yes. Liel, or maybe he's not here, or she is not here.